All right, so we're starting. We're gonna talk after you guys. How many of you are pretty much done with the what is it? Mass properties analysis, right? How many of you made those parts? Two of the three done. Is it four or is it three?
There's four, yeah.
I thought there was four. So you're two of the four. Okay, I thought so. But anyway, that's fine. All of you have a little bit different level of inventor skill, which is fine. And so it's all right. Hey, this is kind of a big deal. I'm live here. And so we're after you make an inventor, and a lot of us have done this in IED, we then made a prototype, right? How did you make that? 3D printed it. That's pretty much, we maybe laser engrave some of it, whatever, but for most of us, that's how we make it. And we'll talk about that, but that's typically, and it's not just a 3D printer because there's other methods to making prototypes. When I was at Stout for training 2-3 years ago, we went to a company, which honestly, if they, let's say I got fired today, I would drive over there and say, hey, I want to work there because it looked like the coolest place ever. Their job is to make prototypes. And so you go to work and you probably don't know what you're going to do that morning. And there's some bad deadlines, like it comes in, they came in last night and we need to make this prototype of whatever, and it's and they talk about it, yay or nay, we can't do it. And most of the time it's, yeah, we can do it. And they're not always working prototypes, but they're something that people can have in their hands and look at and go, oh yeah, that's something that, and then they can take it to market research and do things like that. So most of them are visual. And so they have engineers teamed with artists, and actually who I thought would be great at it, my wife. Because she's got the artistic and then the problem solving of how we can quick make it. They'll make it look like it and not even use the same material. But and so that they can create that prototype. And they had 5 3D printers that were all probably together worth about $1 million. They had just about every additive prototyping machine available to them. And they're not that much fun to look at because it took, and so usually what would happen is they'd get the idea, they'd make it in Inventor, or actually I think they use SolidWorks, and then they do the 3D print overnight, and then the next day make it, and then they'd have to, there's a deadline of when they needed to ship it, and then go on. But that's basically doing a prototype. Write this down. You see, if you look at our problem solving process, we kind of went through it. Define the problem, generate, concepts where we're brainstorming all these ideas. Then develop a solution, narrow them down to one, and construct and test a prototype. So step 4. And it's used to test, improve a design concept by making actual observation and necessary adjustments. Prototype and model. Anybody know the difference? Flip that around. Prototype is working. Model is something that they can look at. So when I was talking about a non-working prototype, that should be called a model. And a working prototype where you can actually get in the car and drive it as a prototype. And the reason why is you see the problem solving process, and I'm going to use the word iterative to help you with your ACT score. But it's basically it's not a linear process. You don't start here, get down here, and be done.
At this time, any sophomore students with the last name beginning A through K, please come to the lobby at this time for your picture.
And it's a rotational process. So you get, just because you're here doesn't necessarily mean that you're going to go down. You might go back and define the problem again. You can construct, test a prototype. Almost, I'd love to say hours, but you should never say hours. They're going back here and they're making changes to it. Very seldom, if ever, is the prototype like, oh yeah, we're good. I mean, I'd say 1 out of 1,000 probably, is where they build a prototype and like, yeah, there's nothing I would do to improve this, And if it is, it's usually pretty simple. And this is all on Google Classroom. I just put it on there. So the PowerPoints. When we were at that machine, and I got a T-shirt from it, but they a lot of times are doing an additive process, but sometimes they were actually carving stuff out of wood and painting it, because that was faster. Foam, a lot of stuff on foam and hand doing it with that. If we look here, these are just rapid prototyping machines, or prototyping machines. I shouldn't just say rapid. And let's move on. Oh, went too fast. Okay, this is what they had, rapid prototyping, these machines right here. They didn't have the computer right next to them because they'd send them away, but they would come in and UV light would hit, and wherever UV light hit, it became solid. And it just kept working layer by layer and layer by layer up. And to be able to do this, you guys know this from IED, you need to at first make the 3D model or have the 3D model. And here's just an example of this train making a 3D model, 3D print of the train, okay? Starts with the file, then they create the prototype after they put it together. It slices it by layer by layer by layer, okay? So when it's building it, you just start on the base and just make this layer and then move up. Make this layer and move up. And of course, it will solidify and then moves up. The speed of rapid prototyping has gotten faster, but it's still not at the point where you hit a button and it just like pulls it out of midair. Is able to poof, make it yet. 3D printing, we know this process fairly well. Here's one where, let's move on. There's all these different types of 3D printing and everything. I'm going to show you a video of where they've made the Eiffel Tower and they just pulled it out, and it's a time-lapse video because it doesn't happen that fast. But it is pretty neat. It's much faster. You're able to pull it out of this liquid and it became solid where the UV light touches and it goes the top up. I don't think I'm going to be able to play this, but I'm going to try. Oh, this is the computer that has the PowerPoint. No. So again, you have this if you want to know all the different types of, I don't feel it's worth your time going through each step, each type of rapid prototyping machine, because if I showed when I learned this stuff in college, all the different machines, they've changed rapidly. Some have stuck around and some of them haven't. And so to learn it, But what I do want you to know is this. It starts out with what you worked on before, with creating a 3D file. And then we're able to take that and make an actual 3D object. Okay? How we do that, there are different processes out there. Some work better in different types of material. Some work better different types of plastics. There's hybrid machines out there now that they're able to 3D print metal and mill it. So now basically they can 3D print and then mill it to within 10,000ths of an inch. Okay, those are the types of machines that I see totally revolutionizing our manufacturing process. So being able to actually build a steel part in matter of, from concept to in hand in less than 24 hours is really quite unique. All right, one more. Have we got our pictures taken yet? All right, and I talked about this already. So as we can see, then we evaluate. Most likely we're coming back here. Okay. Understanding RP, rapid prototyping, and the thing I would be fearful about going into this rapid prototyping company or model making company would be that these machines are getting more readily available and their company may become obsolete because I can now afford a $1 million machine that is now, or it was $1 million, is now 100,000, and be able to rapid prototype my own prototypes, okay, by a click of a button. As we've talked about, it basically is like a deck of cards, okay, stacked up. Make the first layer, card number 1 out of 52 and just keeps moving up. And this is what we're talking about when we're talking about what we use in the 3D printer here. And all right, Z-axis is up and down, Y-axis, X-axis, okay? Somewhat basic, right? If we took that graph paper that we had in math class, we'd put it right at X and Y coordinates, right? We just put it right there with the Y coordinate being this way, X being this way, and then Z going up. That's nothing new, right? Now we have a dual extruder. What's the benefit of that? Okay, one is we can take a water-soluble plastic that we can build a support, and then we can stick it in the sink or in a pail of water. It dissolves, and the supports. And before, yes, you would build supports with that plastic, and they were designed to break away, but it was never smooth and nice and clean, like when you use a dual extruder. What's another benefit? Two different colors, two different types of material, if they will adhere to each other. It is possible that we can 3D print something that has, a different type of plastic, different. So as this gets better and better, you might see 3, 4 rolls, okay? And being able to use different types of plastics. The hard part about that is the different melting points of different plastics. So some you might have to heat up more, some you might not. Those types of things are what they're having to work out. Like you have these two very close together, and all of a sudden this one needs 100 degrees more heat to melt. Well, then it touches the other plastic and it melts it. So, there's lots of things that can happen, and they have gotten so much better at 3D printing. It's not even funny. I've now having students with 3D printers at home, and it used to be such a novelty. I remember going into a room that had a 3D printer in, and we'd see it, and then we'd come back in 12 hours and they were maybe moved up an inch, and that was the only 3D printers available. Now, like I said, I'm having students with them. These are different types of thermoplastics. Does anybody know what thermoplastics means? There's thermoset.
Thermoplastics can be melted or deteriorate.
Yep. And so the difference, like your pot and pan handles, right? Made of plastic, but they don't melt. Well, they will melt, but they melt at very, very high temp and you're not going to reuse them. Where thermoplastics, you could reheat them and they would melt down. We could take all that plastic that we use for 3D printing, chip it down, melt it, extrude it into that lining and use it again. And there's ABS, PLA, and PVA. Okay, now ABS is what a lot of your plastic toys and stuff are made of. Okay, we use ABS. The maker box would only take PLA, polylactic acid. Okay, the nice thing about PLA is it doesn't smell. And they're getting really good at PLA because of 3D printing. They're really working hard at making it a more solid plastic, but it's still not as strong as ABS or nylon or the other things that we can use. And the PA, I believe that's the water soluble stuff. Am I right? Yeah. So and those are made for supports or where you want voids, where you want hollow spots, and then you can then use that. There are many others. As you can see, this is God, what a bad colored slide. All right, so how you put your part on the base matters. So for example, this is a, what you would call this, geometric shape. It's like a pyramid, okay? Let's think the Egyptian pyramids, okay? You wouldn't put them with the small end on the bottom and then build out because you would need all these supports, right? So you would flip it over and put it base. So just because, here, let's use this as a good example. If I was going to 3D print this part here, I won't take it and make it like a little bit every layer, just a little bit, but it's difficult and you might as well do it like this, right? Even if it's designed to be like this, okay? So, or on the side even, if it was designed to be like this, well, you wouldn't 3D print it like that, okay? So that's something that you want to think of when you're putting into the 3D printer. So you're always looking how you can optimize and use the least amount of supports as possible. Here's an adaptation to the Automo blocks that was 3D printed, and just using it to try to optimize, and we'll go through that. You want to make it so that you can use the least amount of support. Now, this is one thing that we haven't done that I'd like to get into a little bit more. We've tried it a little bit, but how we can, so the finish is optimal. And then there's also, you can stick it into different chemicals, kind of smooth and round the edges so that, it's not so rough and looking. Now, when you're printing a 3D, the infill, this is how close these are together, okay? And it's basically like honeycomb. I believe I've read somewhere that they use that design of two-type making, but you can pick many different infills. Know this, the more infill, the longer it takes. Typically, should be the stronger the part, though. Okay, so you have to go through that and kind of decide how strong is this part. Just a model that we're going to look at, or is it something that we need to use for to use as a part? Then you're going to want to increase your infill, take longer. Let's go back. All right, ABS shrinkage. They all have shrinkage. And so that needs to be considered. We made cell phone cases one time. And was that with you? And we'd make measure the cell phone. We measured it just exactly right. Then we built the cases and it shrunk and this phone wouldn't fit in anymore. Okay. So that has to be considered. And so the type of material you're using, you can look up the shrinkage and get pretty close to how big you should design it and create it and print it. Okay. I would design it the correct size and then scale it when I have to use it for the print. You can bring parts together. This was done a lot where they would print, they'd have 5 machines all printing stuff that they were going to join together for a prototype. Okay. And then they would use like super glue just to join them. Again, not a working, so they were doing it for model. Here's an example of that part they used for like a wind tunnel. They made the wing for the wind tunnel to test on it. Different cams. All right. Any question about the prototypes? All right. So now I'm going to give